that's a very exciting session. So I want to start this panel with a couple of high-level questions. Like I mentioned at the beginning, so we see that there is a new requirement to our traditional network. So let's first do some comparison to what these networks were doing and what's different now. So I would like to first ask Shiv. So as the network, the edge network evolves to support AI and more immersive content, how do you see the role of traditional CDN is in this new era?
That's a great question, Ying. I think let's probably understand what is special about traditional CDNs and then try and contrast with this new wave of computing that's coming in. So traditional CDNs have been around for a long while. At this point in time, they are really well understood in terms of what they really need to do, right? So we can boil it down to, I would say, three basic set of parameters. Minimize the amount of network throughput that you're trying to do with the CDN, improve the cache hit rates, and then try and return these response objects as fast as you possibly can. So those are, I would say, the measurements that traditional CDNs tend to get measured by. And now the makeup of these machines is also largely known. So you've got machines with a lot of storage, SSDs and NVMe, a lot of memory, and then a lot of, I would say, good I/O connectivity to be able to pump data back and forth. So now if we try and compare this with, say, the edge that we talked about and the new computing needs, you're now going to have a lot more general purpose and sometimes specialized GPUs coming in to be able to take on some of the newer workloads. The storage is not going to be as necessary as, say, the raw compute power available on these machines. The power throughput of these machines are going to be a whole lot different. I mean, to kind of conclude my answer, right, all of these applications are additive. We do see traditional CDNs still being around, serving content. The evolution is all additive, so it's not a replacement. So we've got to adapt and ride the wave and be able to build machines at the edge that can take on compute-heavy workloads.
That's a great answer. I really like the fact that it's additive, right? Like we are not like doing everything from scratch. Yeah. So then there is a follow-up question, perhaps to Lee. So we have done a lot of optimizations in traditional CDN, cache being the very well-known one, and it has shown its success. So what do you see as like the role of caching, particularly given really the custom nature of AI and inference workload?
Yeah, good question. It's going to be very interesting. I think as we look at the two different paradigms, we talked earlier, CDN is very good at caching content. That's what it's here for. We can offload the backbone with huge volumes of traffic, and really the locality of this is more about how do we help the internet keep up with that demand. As we move on to some of this less cacheable piece, it moves the challenge less from the internet-facing side of the infrastructure, but more to the backbone side of the infrastructure, as you heard, given that lots of this is less cacheable. And so what we're really looking at here is how do we move the paradigm of compute closer to the edge of the network so that we start to offload the backbone. So bringing new types of GPUs, new types of ASICs and other technologies to much closer to the edge of the network.
Thank you. Yeah, so I think these both answers kind of touch upon this very important thing about new hardware, and then there are also the software layer we need to impose on top. So I would like to ask Ron about, like, in the HPC world, you actually talk about interesting layers, hardware, how it's evolved software, and then applications on top. Like in your work or in HPC domain, did you guys do any of this cross-layer optimization? Do you see that is kind of one of the important approach to tackle the future, like AI, ML challenge?
Yeah, it's a great question. So if you look at what we've done in the HPC space over the last 20 years, a lot of the things that we've done have been analyzing our applications and algorithms, looking at our software layers and understanding how to map those better, and then making hardware advancements through co-design to try to match those two, right? And that was fairly straightforward to do for about 20 years when there was not much innovation, frankly, in the space. We had MPI as a programming model. We had modeling and simulation applications that use that, and we had high performance systems that look pretty much the same. Distributed memory, small core counts per node. Not a lot of innovation in the space. Opportunities today are all over the place, right? This is the big challenge for us: is which of those opportunities is going to have the best, how can we pursue all of the different opportunities that are out there? A lot of the co-design frameworks that we've developed, a lot of the simulation technologies that we've developed to be able to look at how future systems are going to behave need to be improved. And we need to be able to do that much more quickly now, because vendors are coming to us and saying, you can have this or this or this or that. What do you think is going to work best for you? And our challenge before was one or two vendors telling us, this is the system we have versus this system. And so being able to have this framework that allows us to do that kind of analysis much more quickly, turn it around much more easily. But from an opportunity standpoint, there are a lot of them out there, I think. This is a great time to be in high performance computing because there's so many things that are happening.
Great, great. Yeah, I think we are all very excited about the speed of change. That's why a part of the reason why we are gathering here. So I want to kind of coming back to the backbone space where we just listened in the third talk. So when there are a lot of new changes happening from our application, backbone as really the foundation that provides connectivity, which is like a stable foundation, right? How would this kind of a variety of requirement, different options that bring into backbone in terms of new requirement? Maybe Jyotsna, do you want to start?
Yeah, I can take this one. It really depends on the kind of workload that we're trying to support. We're trying to support multiple different types of workloads. So whether that workload needs real-time data versus non-real-time data, how much data is required, what kind of models are being run with that data, whether it is being used to serve production traffic or whether it is for experimentation purposes, all of these have different requirements on the backbone, whether that's in terms of the amount of capacity that is needed, whether that's in terms of reliability of the network. As you can imagine, production needs higher reliability than jobs that are being run for experimentation or testing of features. So it really depends on the kind of workload that we're trying to support. We've designed a backbone so that it is easy for us to pivot and support multiple workloads in the same region.
And Abishek, do you have anything to add?
Yeah, I think Jyotsna touched on a lot of the key points. So the other thing I might add is it's also about like on the ML space, right? So I think a lot of it is, there is a lot of experimentation that goes on to figure out which models might benefit from what kind of data sets. So getting better at that prediction then cascades to better stability of like which data needs to be kind of placed where, which then has better stability for how backbone can dimension. So this is also why we want to kind of make sure we build the envelope and kind of have that foundation like Ying was talking about to absorb some of these inorganic drivers, which can be a bit hard to predict. But once that any of these kind of scale, we want to pay closer attention to how we can do that more efficiently. So.
Great, great. Yeah, I think that sort of gives us a great idea, sort of reflecting back to compare to the previous traditional network and what are the new challenges. And I think in the talks, there are many kind of interesting technical details. Next, I would like to maybe zoom into one or two aspects and maybe use this opportunity to have the speakers elaborate more. Maybe we can start with the HPC space. So Ron, you talk about a very interesting observation of this higher level API and the low level API, and they don't match. And it seems there are a lot of efforts trying to align across these two abstractions. So that gives us a thinking about like, what about ML world? We all know like collectives is really the abstraction, the new abstraction. And do you see this kind of similar mismatch also has happened or would happen in the new ML AI workload? And if so, then is there anything that you guys have? What are the practices or principles that we can leverage from your practice before?
Yeah, so great question. I mean, collective communication has been one of the fundamental things that MPI has done really well. That's what we've optimized that environment to do, whether it be broadcast reductions or some of the other more sophisticated collective operations that happen. This is another one of those challenges where if you look at the complexity of the node, a lot of the collective communication optimizations that we've done in HPC are not necessarily in the fabric, they're at the endpoints. And so there is this challenge of what happens in the fabric, what happens in the mesh and on the switches versus what happens at the endpoints. For a lot of what we see from AI ML at this point, there's a lot of bandwidth optimizations. And so you're trying to find the highest bandwidth path across the network all the time and understand the complexity of what data is moving and where you have shared links versus dedicated links and things like that. And understanding the complexity of all of that, whether it be at the node in the memory system, the internal networks on chip, on package, and then into the fabric, coordinating all those data movement, all that data movement is really challenging. And so there's a potential there for all of those things to be uncoordinated, which is challenging because you have to have the mechanisms in the right places to be able to do that. But then there's also a challenge of if the fabric does a lot of that work, how do you manage that, right? Because from an endpoint perspective, another part of this component is making the decisions. And so I'm subjected to decisions that I'm not making. And so this idea of no central coordination of how you do data movement and how you do some of these operations is also challenging. You'd like for some of this to be automated, but you also want to be able to control it in some sense. And so I think there's an opportunity for mismatching those layers because everybody, the different components want to be able to control what's in their domain, but they don't see the connectivity across the entire system sometimes.
That's I think it's kind of very interesting to hear about orchestration, which is kind of very important here to achieve optimality. Management is always challenging. So maybe the next question would be to the edge side. I think because of the introduction of the edge computing, there are potentially new kind of security challenges. One particular angle is how do we provide isolation? So this is also a part of like orchestration management. How do you provide segmentation from unsecure environment? What are the policies that you need to use to support your tenancy control? Maybe Shiv, can you?
Yeah, sure. Yeah, thanks for the great question. So I think there are two parts to this question, right? So there was the latter part around tenancy control, and there is the part around security. So let's maybe take a look at them individually. So tenancy control is all about, we've got this edge, we've got a set of applications. We want to make sure that an application's usage is within bounds with respect to how much resources it could go on to consume, right? So if an application ends up hogging, say, either the compute or even the network resources of, say, the host or the cluster that it's running on, that's going to have a regression on some of the other co-hosted applications in the same space. So to monitor all that, we do have tenancy controls on all of these critical resources, GPU virtualization, CPU virtualization, and also having caps around the amount of network, both in or out, that an application tends to use. So we've got all of those primitives around tenancy control to be able to make sure that an application's usage is kept within bounds. Now, security is a deep and a more interesting topic, and there are like many layers to it, right? It starts all the way from, say, your operating system that you may want to harden with a lot of measures. That's a conference in itself and not worth going too deep into. And then you've got the runtimes and the container systems that also require a level that bring in a level of security and isolation to be able to keep the compute within the bounds of the virtual space that it's creating. So we leverage that. And then thereon, we've built other stuff to be able to create virtual overlay networks so that the real physical network is not known to the application, and each application runs in its own network cocoon of sorts, so that we can then easily enable, disable, throttle, rate limit the amount of say, network usage that it has. So these are all like these layered policies that we have in place and mechanisms to be able to bring in both access control and security.
Great, great. Yeah, it seems like sort of a lot of this virtualization and overlay technique can play a very important role here. What we just kind of heard about two discussions more related to the micro level of the topic. So I want to go back and ask more about the scale challenge, right? Networking at scale, coming back to the topic. So we all know like training is very hard. Like it actually imposes a lot of scalability challenge, and we just heard about it from the backbone. So Abishek, I want to ask you about what about inference? Like if inference goes also on scale, what are its implications?
Yeah, thanks, Ying. So yeah, that's definitely an exciting space that's growing. But before we kind of look at what the future might hold and what we're thinking about, I think it helps to also look back in time a little bit. So we've been operating and running AI workloads for a longer time, right? So the ranking and recommendation models, all powered by AI, have been actually running, and we have like models that have been trained and are being served. So if you think about those workloads, they are already something we support on our backbone as well as through our edge infrastructure. Now, as we have these new workloads that are kind of flavors of this that are starting to grow in popularity, right? So Gen AI is a good example of how it has become more popular more recently, has a different dynamic of how it might show up on the backbone, because the models are different, what the use cases are kind of different from, say, recommendation models. So what this all means is, if you kind of step back multiple layers inside the stack of how we actually serve this traffic, our service and call graphs can be quite complex because these are large, complex models at scale. So which then translates really to how do our services, our backend services, actually talk to each other to enable this. So, and typically inference is quite kind of sensitive to latency, as we all know. So that then means, how can backbone actually ensure that we're meeting the performance guarantees? And this is one, again, that goes back to that theme or tenet about we really need to work across the stack. And in this case, I would say work across edge, work across like, where we need to get the requests served to the users, and how can we do this in a more intelligent, innovative fashion. So kind of bluntly put, like we want to make sure we meet the constraints and objectives, and that's like priority, right? Like we cannot kind of miss on that. Once you get there, then can we think outside the box or look across domains, whether it's network domains, or you could even think about like compute or storage domains again here, because some of the models, as we know in the industry, are growing at an exponential rate in terms of their size and complexity. So that also has us rethinking about what this means from a compute standpoint as well as we serve these workloads. So it's kind of all intertwined and coupled, as you can imagine, but we want to make sure from a network backbone perspective, we enable and kind of unblock, and then come back to the drawing board to figure out how best we can kind of serve this that is more cost efficient and kind of like making judicious use of our precious resources. So, yeah.
Great. Since you throw the ball back to edge, so let's ask maybe Lee again. So I'm glad that you also brought up power, which is definitely one of the key constraints, physical constraint. We heard there are a lot of kind of a potential new requirement to edge. Now we need to build large compute clusters. So what do you think about really the power requirement, and how would you dimension this problem?
Yeah, great question. I think power is the biggest constraint for all of us, whether this is data center or edge. We're all competing for the same resource. And if we think about traditional CDN or edge CDN, this is fairly low power in comparison to now stuffing GPUs inside these machines. And so we've been able to sustain growth of our CDN in the traditional carrier hotels really close to the peering. And that's served us very well. But now we're having to pull out of some of these buildings in order to build these larger, more power-dense clusters. I think the interesting thing here with the differences between data center and edge is Data center, we have very defined blueprints. We deploy huge, hundreds of megawatts at a time of compute, and that's how we think about it internally. But when you start to think about the edge, they're not really all dimensioned in the same way. It's very much dimensioned based on the number of users in that market. We're not going in just deploying 100 megawatts of GPUs in some market somewhere because that's what we're going to deploy. We're very much looking at how many users are in that market, how many do we think are going to use these services at peak, and what's the peak that we need to build for. Similarly, now tiering our applications too and thinking about these lower latency applications that really need to be as close to the user as possible versus some of those applications that can be slightly further away where maybe we do utilize the backbone in order to stitch some of these experiences together. But ultimately, we're all, I think, everybody in this room likely has power on their mind at this point, and we're all kind of competing for the same resource. So now it's about how do we build the right thing.
Great, great. So kind of we touch upon like the scaling challenge. I think a couple of the speakers, the panelists, just mentioned about the optionality. Like it seems there are a lot of changes, like Ron was pointing out, that we need to really act fast. So again, from the backbone perspective, from Matter's workload, we have a variety of different AI training models. So I want to maybe ask Jyotsna this question. From backbone perspective, how do you see the optionality or variety of AI workload? What are their different requirements on the backbone?
Yeah, great question. Abishek touched on this in our talk about building enough supply so that we are able to support a variety of workloads. If we talk about the physical layer first, we try to enable all our regions so that it can support whatever kind of workload that the product groups require. And that might mean a certain number of paths that are built to a region. It might be higher for anything that is serving production workloads as opposed to something that is just used for experimentation of features, as I'd mentioned in the earlier point as well. So we try to keep this in mind while building our backbone network, while building and designing it, that we are also keeping in mind efficiency. So while we want to kind of build to the ceiling, we are being efficient about it. And we start off with a certain number of paths. And then as needs change from product groups that require that region to be able to support a higher amount of capacity or move larger data sets, we have a plan in place where we can phase in some of those additional fiber paths that need to be built to that region.
Great, great. Yeah, I think you touch upon a very interesting point that different data centers actually they are having different characteristics, and they have different requirements on backbone, and that depends on applications. So coming back to the HPC world, which serves a very different type of applications. It's very interesting in your talk, Ron, that you mentioned the comparison briefly with traditional data center network. Because of the nature of the applications are different. What we see, I want to kind of hear more about what's the thought on the similarity and the differences and the potential opportunities to learn from both.
Yeah, so it's been interesting to see the convergence of HPC networking and traditional data center networking that's going on. So this, I touched on this a little bit. It's an interesting thing both from an economic perspective and from a technical perspective, because if you look at, for example, I'm old now, so I tell the story of spending a good part of my career arguing for network offload capability for high-performance computing systems, and that designing and co-designing network interfaces to actually understand the protocols that we need in HPC and do them efficiently was really fundamental to making HPC systems work well. And talking to the traditional data center networking folks, that was never something they were interested in. It was never economically viable. It was something that they just didn't think was feasible. And so I spent a lot of time and a lot of effort and a lot of research showing the benefits of it. And then I kind of gave up on it, and 2 years later, SmartNICs were everywhere. And so it was, well, what happened? And it was, well, they found it, in the traditional data center where you're offloading virtualization, virtual network processing to the offload, to offload CPUs, we were trying to do it to make overlap of computation and communication more efficient for HPC. Same thing ended up happening in traditional data centers, but for a different reason, right? And so those are the things where we're coming together. We may not have the same reasons, but we need to find the common technology solutions that are going to benefit both of us. And I think more of that's going on. You look at, traditional data center use of RDMA technologies over just standard TCP, Ethernet sockets and kinds of things like that. So there are these places where traditional data centers and HPC are starting to more align to capabilities. And so that's what's exciting for us in HPC, is seeing some of those technologies, regardless of how long we've been waiting for them, to see some of them show up is great for us.
Great, great. Yeah, it's very interesting to see that there are different problem spaces, but then finally we're kind of converging, sharing similar challenges. I think the same thing happened at Edge as well. A couple of years back, it was a very hot topic for mobile edge computing. A lot of 5G, 6G things, probably still in a lot of people's memory. So now we're also talking about edge computing from AI, supporting AI, immersive workload perspective. Lee, could you tell us more about, compared to all the innovations or trends, technologies that in the previous edge, mobile edge computing community, anything sort of, what's the difference, what's the similarity, anything you think we could borrow?
Yeah, no, it's a really interesting topic, and this has been hot for a long time. MEC was the next big thing. 5G was going to enable all of the applications up the wazoo, but I'm not convinced we saw a huge amount of this land. I think for us, we compare kind of the mobile edge compute of old more with our M&A type deployments. Small, very focused deployments, very deep into the network that can service a small number of users or a smallish number of users. I think what we're talking about now, though, is something much larger. We don't want to be deploying huge, 20 plus, 50 plus, 100 plus kilowatt deployments inside mobile base stations and all of these kind of things. Yes, we're close to the edge of the network, but we're much further back. What we're interested in really from our point of view at Meta is interconnecting people. So deploying something inside one network doesn't largely help us with that. Those are some of the experiences we're talking about building next. So what we're looking for really are deployments that can service multiple different networks, because not everybody in the same town has the same carrier or the same broadband ISP at home. But really, some of the challenges are the same. Low latency so that we can have chatty applications that can seem very fluid and be very interactive. So I think lots of learnings taking from there, but when we think about things like IoT, small sets of messages going back to a database or something similar. Now with things like Metaverse, we're actually talking about fairly high bandwidth applications at times that do require modest latency. We could be talking, 15 megabits of bandwidth and 30 milliseconds of latency. That's actually quite hard to deal with when you think about this on scale. I talked in the talk earlier about a 40 millisecond average round trip from user to edge. The keyword there is average. Achieving that everywhere is really, really hard. And so that's kind of the paradigm that we're going after now, and why we're building this small pop type topology so that we can go deeper into the network.
Great, great. Thank you. I think we've heard a lot of dimensions, right, we brought in this session. So I want to kind of step back and really think about, we see these new models, new applications that has imposed new requirements to network. I want to sort of end this session with one high-level question. If you wish the network has certain things to solve your problem, use one word to describe it, what it would be. It could be capacity, it could be flexibility, whatever. So starting with Shiv.
I mean, it's a great question. I mean, the quick short answer is probably we need to have a good prioritization at all layers of the network to be able to drop packets and load shed and prioritize quickly. So that's probably my top of mind.
Lee?
I think unlimited and maybe pushing the boundary a little bit here, unlimited and free power, they would be the two number one things. How nice would that be?
Cool. And Rob?
This is really challenging to say one word that would be everything I wanted from a network. I talked about complexity, and so I'm going to say simplicity, right? One of the things that we need is to think about simplicity for the things that we need to do. Everything is moving towards more complex systems. We need to figure out how to make things more simple, whether that's modularity or programmability, whatever the technique is. But I think simplicity is one of the things that we should strive towards.
Jyotsna?
Yeah, I think given that power is kind of constrained, I might think about network hardware becoming more power efficient so that there is less power that we need to dedicate to networking hardware and more of it can be dedicated to training and inference.
Great. And Abishek?
So yeah, I would say flexibility maybe as like the one keyword, because as kind of network foundation, we want to make sure we can support like kind of changing needs, and that's the best way we kind of unblock product innovation. And so that's a little bit of what I would kind of have us kind of be open to. Are the constructs that we have still helping us? And if not, we shouldn't be kind of shy to go back to the drawing board to kind of rethink how our principles are. And that's probably what I would leave us with. Yeah.
Great. That's a very great conclusion. So that concludes our session. And we will have the coffee break next. And the speakers are all around. Please feel free to come and talk if you have any further questions. So without that, let's thank speakers and enjoy the coffee break.